So now what we want to talk about is how can DFT play a role in processing of discrete time signals using discrete time systems. In digital systems, when you implement a system, you're given Hn, you calculate the output Yn, and the input is Xn. The output is Xn convolution with Hn. Okay. Now, if Hn is a finite length impulse response, so let's make the assumption that Hn is approximately equal to some length n, and Xn is approximately equal to some length n signal. Okay. What you need to do inside a digital system, for example, if you open up MATLAB and you say, I want to do convolution of these two sequences, you will have to use the convolution formula, which is y of n. So we are going to work with the finite duration version of convolution formula. So that's x of m, h of n minus m. Okay. And n will go from 0 to 2n minus 1. Now, if you do that, you will again, I'm going to ignore exact constants, but if you do the computations and if you ignore the fact that some of these values are 0, again, what you are looking at is that the total cost of convolution, use linear convolution using direct formula has computational complexity of around of order n squared, which means that some constant times n squared, because again, for each little n, you are doing n multiplications, n minus 1 additions, and you are going up to 2n minus 1, again ignoring the fact that if you are multiplying with 0, that can be done in a really fast fashion. It will take order n squared amount of time to do linear convolution using the formula directly. Okay. So what we instead want to do is use DFT, and when I say use DFT, effectively use the FFT algorithm to compute DFT to do linear convolution. So we want to reduce the cost of doing linear convolution by resorting to DFT/FFT. Because in that case, the idea is that that will reduce the cost to order n log n to the base 2, which is much smaller than n squared for appropriate values of n. Okay. But the question is, how do we do that? Because the only connection that we know about is between DFT and circular convolution. Whereas we are interested in doing linear convolution. So the answer to that actually lies in the fact that circular convolution can be made equal to linear convolution by choosing appropriate values of the number of points that you want to do circular convolution. Okay, so the answer is circular convolution is related to linear convolution as long as we use enough points for our circular convolution. So to make that clear, I am going to say that suppose let's stick with xn. So xn is length m, okay, which means it goes from 0 to m minus 1, and hn is length n. Now, in that case, if I do linear convolution of the two sequences, then we know that the output will be of length m plus n minus 1, length of one sequence plus the other sequence minus 1. And if I do the circular convolution of the two sequences, Gn, and let's use the length L as the number of circular convolution points, times Hn, where of course I have to make sure that L is bigger than or equal to max of m and n. So the length of my circular convolution has to be bigger than length of both of the sequences. So this YCN is of length L then. Okay. And in general, YCN is not going to be equal to YLN. The circular convolution output will not be equal to the linear convolution output. Okay. In particular, if you are interested or if you read the optional reading, what ends up happening is that the circular convolution is equal to actually aliasing of the linear convolution. But what happens is that if we take L big enough, if we take L bigger than the length of the linear convolution, so if we take L bigger than m plus n minus 1, then this is no longer the case. Then actually circular convolution is identically equal to the linear convolution. Effectively, you are avoiding the aliasing of linear convolution by doing that. Okay, so I am using L at multiple places, so let me actually make it simpler. Let's replace this L by P. So now hopefully it will be better that you are computing a p-point circular convolution, okay? And if your p is bigger than or equal to the length of your linear convolution, then circular convolution becomes equal to linear convolution. And if that is the case, then that means that I can say, so now fix some p bigger than or equal to m plus L minus 1. This means that G or Again, I'm using G when I should be using X. So X n P point circular convolution with Hn is the same as Xn linear convolution with Hn. And now the question of how we can use DFT for fast computations of linear convolution becomes simple, because we know from the convolution property that the DFT of this thing, P point DFT, is equal to xk times hk. Okay, and if they are equal, then both of their DFTs should be the same. So this will be xk hk also. So that provides us the basically guidelines for how to use DFT to compute linear convolution in a fast fashion. Okay, so we'll be given xn length m and hn of length n, and we are asked to compute linear convolution in a fast fashion. The steps are: first, we pick some number p bigger than or equal to m plus n minus 1. In general, you want to pick a number which is a power of 2, and it satisfies this inequality, because we talked about FFT really is the fastest when you have a power of 2 involved in it. Now, the second thing is then you compute T point DFTs of Xn and Hn. The third step will be you multiply the two. So if Hn has a DFT HK, XK, sorry, and Hn has HK, then you multiply them to get XK HK equal to YK, K from 0 to P minus 1. And then you take the inverse, the P point inverse DFT of YK to get Y of n. Okay. And then that Y of n is going to be equal to Xn linear convolution with Hn. So the picture that you get is exactly the same as the convolution theorem picture that we drew, except that you have to pick your P to be appropriate value. Now, why is this a faster operation? This is only a faster operation if 2 and 4 are computed using FFT, then it will be a fast operation. If you use that direct DFT formula, then of course it won't be fast. Okay. And when people talk about, since you are using P which is bigger than the length of the sequences, effectively you are zero padding the sequences to make them length P. Okay. In particular, this DFT based processing is a centerpiece of modern wireless communications that uses a modulation scheme called OFDM. Okay. In your cell phones, this particular operation is happening all the time. Okay. Now, we won't go into the details, but I just want to point out that sometimes what happens is that our input signal, we don't know how long that is. You want to do real-time processing, your HN is finite length, but sometimes XN is of unknown or infinite length. So in that case, of course, you cannot use this formula because p greater than or equal to m plus n minus 1, the factor m is infinite now. So in that case, what you do is actually chop up your input signal into pieces and then stitch those pieces together in a careful manner. Okay? And there are methods available to do that. They are called overlap add or overlap save methods. Exist to carry out DFT based processing in that case. I just want you to be aware of these things. We won't go into the details of either one of those two methods.